My name is Maximilian Ulmer and I'm a research scientist at the German Aerospace Center. I'm excited to introduce you to our latest work, 6D object pose estimation from approximate 3D models for orbital robotics. In our approach, we combine deep learning and classical region-based refinement to tackle the challenging problem of image-based 6D pose estimation in space. The work was created with my colleagues Maximilian Durner, Martin Sundermeier, Manuel Stoiber, and our advisor, Rudolf Drebel. The motivation of this work is to perform highly accurate 6D pose estimation from images in space, which is a central component of autonomous robotic on-orbit operations such as servicing, debris removal, and assembly. This means that we want to accurately estimate both the rotation and translation of an object relative to the camera given only an image and an approximate 3D model of the target. A key problem of orbital perception are the extremely challenging visual conditions such as reflections, high contrast, and low signal-to-noise ratio. In addition, this work focuses on the realistic scenario that only an approximate 3D model of the target is available, which is missing many geometric details and textures. At last, real annotated training data is extremely costly, especially in space. Hence, we operate on a pure sim-to-real setting on synthetic training data. Our approach can be divided into 4 steps. First, we acquire a region of interest. Next, we estimate correspondences. Third, we generate pose hypotheses. And last, we refine all hypotheses and choose the most probable. Now, let's quickly dive into the individual blocks. We utilize an object detector, which is trained using specialized modules which simulate specular reflections in the exceedance of the camera's dynamic range. To generate regions of interest during training, we use the ground truth bounding boxes that we randomly shift and scale. This helps with imprecise bounding boxes during inference, which often happen in the most difficult of conditions. In such conditions, parts of the target are often not captured by the camera sensor and simply resemble background noise. Once a region of interest is determined, we use a deep neural network to establish pixel-wise correspondence between input pixels and 3D model points in the inertial frame of the object. In addition, the network predicts a confidence matrix and an auxiliary segmentation task to increase robustness to object symmetries. This alone is enough to estimate a 6D pose using the well-established perspective endpoint algorithm, short PNP. However, we found that using all possible correspondences greatly deteriorates the performance when using an inaccurate 3D model and when many visual features are corrupted by reflections or shadows. Our solution is to train the network to estimate an additional pixel-wise prediction error. This allows the model to reliably localize regions of high error, here visualized by epsilon 0 to n on the bottom left. In this example, epsilon 0 uses all correspondences in the orange shape to calculate a pose, while epsilon 1 only uses the correspondence pairs in the blue area. This way, we collect some hypotheses with a very low predicted error and other hypotheses with a very high associated error. Finally, the iterative pose refinement builds on previous work on tracking. In essence, this class of algorithms attempts to differentiate between a foreground and a background and then tries to find the best pose that explains the segmentation. Previous approaches only used classical features such as color histograms to optimize the 6D pose. Such features, as we are showing, perform poorly in the visual conditions of space. Hence, in this work we introduce a novel pixel-wise posterior based on color histograms and learned features from the decoder of the previous step. Together, the feature space is discriminative even in very low signal-to-noise ratio images. Due to the probabilistic nature of the algorithm, we can calculate a probability of each refined hypothesis and finally choose the most probable pose fit. With this approach, we were able to achieve state-of-the-art on the challenging satellite pose estimation dataset SPEED+ and won the corresponding challenge in its post-mortem phase. In addition, we show in various ablation studies the robustness of this method, even with highly deformed 3D models. Here are the results in detail of the SPEED+ dataset. Notable are the teams Lava and Tango Unchained, which were the best performing teams during the live phase of the challenge. As seen in the table, we achieved the best score for translation error, rotation error, and pose accuracy. The code of this project will be available on GitHub, and please find more details in the paper. Thank you so much for your time.